Hey there. Oh cool. It looks like everything is capturing. Excellent. Anyway, I'm gonna be a fish today because frankly it's still easier. Um, but I'm gonna at least show you what this is the setup. Uh, I'm not all done up and all lit up and whatnot. But there's always a cat, as usual. But yeah, well, let's dive in. This is probably gonna be the last week I'll do fish stuff, just because we're about to get into stuff I pre-recorded earlier. So yeah, hello, and cool. Oops, I forgot to turn off a fountain. I'll be back. Okay, we're back. Introduction to item response theory. This is the most Tuki's done with me. So this is the most technical unit we're going to have in the entire class. After this, next module is like way gentler. We're going to kind of like, this is the peak, and we're just going to be able to enjoy our successes together as we cover practical test things, personality assessment, and intelligence assessment, and yeah, so item response theory. Here's the roadmap for today. So we're going to talk about item analysis in general, bridge it back to a classical test theory, and then go through the item response theory basics. There's going to be a lot of math, and I know that. I also know that you all don't have the prereqs for this level of math. And so I'm showing this for the half of class that does have the background to do this kind of stuff, because this is the kind of stuff I do. But I also recognize that this is not what typically people think of with testing, even though it's the core of what it is. So I will be very, very gentle in the assessments and not have you have to like be able to do the math that I'm going to show you today. But I want you to be aware that it exists, and I believe in every single one of you that you are capable, because you've already covered factor analysis, and this is just actually it's an older, more European version of factor analysis. So yeah, we'll talk about the item response theory basics, go through some of the assumptions, talk about how you actually get these estimates and what they mean, and then we'll dive into interpretation and scoring. And that'll wrap it up. Okay, so what is item analysis in general? Well, item analysis provides a way to measure the quality of questions. So it gives us a way to see how appropriate those questions were for the respondent and how well they measured that ability or trait. And as our discussions and comments on Canvas have indicated, there is a wide range of item quality. There are good written questions, poorly written questions, as well as like questions that are more and less difficult than others. There's a lot of variety. So beyond that variety, item analysis allows us a way to reuse items over and over again in different tests, and allows us to incorporate that pre-existing knowledge about how they're going to perform. And they end up creating a population of questions with known properties. Pragmatically, this is a test bank, but it gets us closer to actually covering our entire content domain by giving us that information. So I know I've shown you this model, this figure before, where item analysis is broken down into classical test theory and latent trait models. We have already covered some latent trait models. Factor analysis is a classic latent trait model, where we're trying to essentially triangulate the measure of that is causing our responses. Now, these models down here, the item response theory models, 1PL, 2PL, 3PL, 4PL, we'll talk about from a like broad strokes theory standpoint. I'll also talk a little about the Roche model, which is a Dutch model, or it's originated by the Dutch, if I'm not mistaken, and it's frankly identical to the 1PL model. Fun facts that eventually will make sense, I promise. All right, so let's review some classical test theory because I know it's been a little bit. So classical test theory analysis are the easiest and most widely used analyses. That's why I started with them in this class. The statistics are easily computable by hand and are, and they're straightforward. And they're, yeah. Now, beyond that, they also are performed on the test as a whole rather than on the individual questions. And although we can generate item statistics, as I've shown you in previous modules, those item statistics can only apply to that group of students that have on that collection of data. We can't really extrapolate. All that it gives us from a classical test theory standpoint is description. That's it. That's why it's really important that we have a representative sample so that we can generalize. But the model doesn't do that work. The data does that work. All right, so classical test theory is based on the true score model, where we assume that error is normally distributed, uncorrelated with true score, and has a mean of 0. And those three components of classical test theory are ARE space OUR are three pieces. So we've got X, which is our total score. And that is a product of, or sum technically, of our true score, so T, and E, our error. That's it. That's the entire model. Three pieces. Now, we've already had some classical test theory stats. So we've had difficulty. That is the item level statistic that describes, well, the likelihood that someone's going to endorse that item or not. Then we've got discrimination. This is also an item level statistic. It allows us to see frankly, how useful that question is at distinguishing between high and low performers, as well as reliability, which may or may not recall was way, way back at the beginning of this semester. Now that is a test level statistic. The other two are item level. So, classical test theory versus where we're going with latent traits. So classical test theory has the test, not the items, as its basis. So although the statistics generated are often generalized to similar students taking a similar test, they really only apply to those students taking that specific test versus latent trait models. So that's also the factor analytic model. Look beyond that to the underlying traits that are producing that test performance. They're measured at the item level and in theory provide sample-free measurement. Here the model's doing a lot more of the work. Now, latent trait models have been around since the 1940s. They weren't really popular till the 1960s, back when computers got better at estimating these. And frankly, so since the 40s, it's been theoretically possible, but not practically so. Without super specialized software and really expensive computing time. But anyway, that's my fun history aside. So anyway, they aim to measure the underlying ability or trait, and that's really broadly defined when I say ability or trait. It's anything that people vary on, like any individual difference, anything that causes performance or responses. So that can be health, that can be like mood, it can really be anything. It just happens to be that the language tends to use ability because classically these tests have been developed in the, well, achievement and aptitude areas and ported over from there. But anyway, the latent trait models produce measures of that trait that are causing the test performance rather than measuring the performance. It's a subtle distinction, I know. And this procedure leads to them being sample free. So they're not contingent on the sample. Now, because the test statistics aren't dependent on the test situation which generated them, they can be used more flexibly. That doesn't mean that if you only have collected data that's a product of a really weird sample that has like 5 people in it and they're all savants, there's still limitations. This model doesn't fix everything, but it's designed to give us more out of our data so that we can then use that data elsewhere, or those questions elsewhere. Cool. So that's going to wrap up this kind of preamble and big ideas section. So I'll see you in a bit. Bye.